So if you haven't yet, definitely pull up the slides. This what we'll be going through today is the MongoDB intro. Looking briefly at the calendar, okay. So general sort of agenda for today, I'm going to be going through the intro to MongoDB slides today. This is likely going to be a longer lecture. Expect this to take about 2 to 3 hours for us to get through this. There's just a lot of stuff to talk about, and there's a lot of kind of off ramps to talk about. You know, what's going on with the industry and other sort of trends, because there's a lot of kind of other things, circumstantial sort of things happening with the industry that are related to what we're talking about today. Okay, so expect bunny trails are a likely thing. Just a heads up. There is a group exercise at the end of this as well, and that goes into kind of working with what we've done today. Basically, it's going to be, hey, let's figure out how to model and build this. How do I put some data into a MongoDB database, but kind of following the same sort of idea that we've been working with his courses and students and grades and things like that, and working through that today. Okay, so that's the group exercise. I do want to go over the lab, your next lab assignment, which is lab 201, and that's one going to have you dealing with an example database that's provided with Mongo. So kind of like you worked with the Sequila and did some stuff there, this will be kind of the same idea with a different database. Your homework for today is to go through the Mongo shell quick start over on Perusal. Cool. So that's kind of the assignments that you need to know about. Tomorrow, I'll be answering questions on the quick start. If things come up, we can try and troubleshoot that, kind of get those things done, and then the main focus is going to be on just having some lab, giving you some time to work on the labs. Okay. In terms of homework there, that's kind of listed, but that's kind of where that lands. Just a reminder, Monday we have Labor Day. Monday's Labor Day, so we won't be having class on Monday. So we'll be coming back on Tuesday. So this lab that you're going to get today is due back, this lab 201 is due back on that Tuesday. Cool. Yeah, do midnight again. So that's the plan there. Okay. So let's kind of get into here. One discussion I might want to have before I talk too much about Mongo is one thing I probably should explain is in the world of kind of web development and software development, there's a lot of different paradigms that people are following to build websites. There's a lot of ones that persist out there, and basically the thing to know is over time we've come up with technologies to do this, and almost none of them have died out at this point. Almost no technology for building websites has died completely. The one exception being something called CGI, and Perl has kind of gone by the wayside. Other than that, almost every technology is still in existence. Most of them. Okay.
CGI as in computer graphics?
No. It was very confusing because you heard CGI as in computer graphics, but there was also a CGI term in terms of web, and that basically meant like dynamically generating websites. So it's an older idea. You won't see it really in the field anymore. But it predates something called PHP. Suffice it to say. Okay. So what we see in the kind of web development world, in terms of talking about full stack web development, database driven web development, there's a lot of different what we call technology stacks out there. So that's a good term to understand. Technology stack. Technology stack is a group of technologies that work well together that you can use to build software. Okay. So your tech stack is kind of the combination of tools that you're using. And so if you want to find out what a company is doing, what a developer is doing, what kind of tools they're using, that's a good question. Ask them this, like, what's your tech stack? So there's some standard tech stacks. So what I want to talk about briefly is some of the more popular ones that exist right now and kind of where they fit, so you know a little about what the combinations of technologies that are out there in the technology stack that we're talking about today. Okay. So first one that you might want to know about is there's one that you may have heard of, WordPress. Okay. This is basically a technology stack in and of itself today. Anybody heard about WordPress? Show of hands. Okay. So WordPress is still pretty popular. It's honestly at this point it's over a decade old, but it's still around. Okay. So WordPress is built on top of PHP, and it's also built on, generally speaking, MySQL. So if you're using WordPress, more than likely you can assume that all of these things are involved. If you're using WordPress, you can say, well, it's probably MySQL and probably PHP. Okay. Doesn't necessarily have to be, but historically it's always been. So a little bit of history there. Okay, so PHP came out in, what was it, early 2000s-ish, and was a very popular technology to build websites with. Okay, and part of that is just that it was free. You literally could get it and start building your websites, building dynamic websites, and it was free. Okay? And that made a big difference. It meant that a lot of people could get into it and do it without having to pay huge licensing fees or run expensive servers. Okay, and so that really helped it take off. The other thing that happened is, okay, these people are wanting to build applications that are completely free, so like we also want a database that's free. So MySQL was the option at the time. MySQL is free, you can use it and pull it down and build a website for it. That was actually unusual. You know, you compare that to Oracle, which is very expensive. You know, MySQL's, hey, this is nice, and it turns out that PHP had built-in support for MySQL. You didn't have to go download some additional software. The drivers for MySQL are straight up built into PHP. Make sense? So they had kind of a buddy-buddy relationship. So this all worked on top of something that was known at the time as the LAMP stack, and it still exists. And this is typically what you're going to see if you're seeing a PHP website. You're going to see the LAMP stack. You'll notice I'm kind of capitalizing the letters, okay? Because each letter in that kind of represents a technology that goes in there. So LAMP, meaning Linux, Apache, MySQL, and PHP. Some people said that it meant Perl. I'd say PHP is a better interpretation of that. Okay? So that's kind of your LAMP stack, is those sets of core technologies. Oftentimes we link in there something called PHP admin. Was commonly used in there to administer these websites as well. But you had all these technologies, and they were all open source, which is really a new thing at the time. It was like the only stack that you could go, only set of technologies that you could go and get and build a dynamic website, a complicated website, a complicated e-commerce store, and have all the tools be free. Does that make sense? Microsoft had some tools, Oracle had some tools. There are other options out there, but they cost a lot of money. So for a little company that's trying to build a website, that was basically the go-to for a good number of years. Okay, and so with that, you saw some growth of some applications, what we call CMS, content management system, which is what WordPress is, really saw growth there. Now, WordPress is not the only one that lives on that stack. You'll also see Drupal, which is less common today, but WordPress. There's still actually a lot of companies using WordPress, believe it or not, a lot of small companies. And there's even a development shop locally here in St. Louis that specializes in that. Like, that's what they do. That's what their company chooses to do for their projects. And they look for clients where that's going to be a good fit. Make sense? Okay. So that's one thing that exists there, and that's pretty popular. Everybody got the notes so I can erase some stuff here? Okay, cool. So that's one option out there that's still very, very popular. Okay? Another option that's out there and popular would be .NET. Okay? And this relies on the popularity of Microsoft. Microsoft's a very popular company. Businesses like working with them. They really like that Office suite. You know, Office 365 is a really popular technology. And so a lot of companies have a pretty tight bind with .NET, including some companies here in St. Louis still have, you know, that's what they do. They do .NET technologies and nothing else. It's okay. So the common factor is that all of the technologies in this stack are all made by Microsoft. That's what everything in there has in common. And so basically you're going to see that in cases where the company's decided to strictly use Microsoft technologies and generally is not open to using other technologies, if that makes sense. And it's actually a lot of these companies that are using that are hard to convince to use anything else. Cool. So that's one thing you need to understand. So what fits in there? Well, C# would be the dominant language in there. You might still see some Visual Basic of some sort, but that exists as well. But predominantly the language of choice is C#. Might also see some C++, but mostly C#. Okay? You're going to see the .NET framework, which is a big collection of classes and libraries made by Microsoft, and you use some of that actually in your second semester, right? So things like lists, things like strings, things like yada yada yada, console, etc. There's a lot of classes in there that are just you get. Build .NET application, you have this whole .NET framework to work with. I think the latest version is 4.5 of .NET framework, last I checked. And so that seems some evolution over time. Other thing that you'll see in there is generally ASP.NET is the dominant technology to be used for building applications. ASP.NET has seen a lot of different iterations and a lot of different versions. So in fact, ASP.NET actually dates back to the early 2000s, but the ASP.NET of today looks very different from what it did then. In fact, if you look at early ASP files, they're basically almost identical to PHP. Okay, early ASP was very similar to PHP. In fact, PHP was basically modeled after early ASP. Okay? And so some things have evolved. The dialects changed. You might hear of something called the Razor syntax, which we use in ASP.NET instead. The newest iteration of ASP.NET is something called Core. Okay, Core would be the current one. Before that, there was something called MVC, which actually previously was what this was taught in this course. Previously, we saw ASP.NET MVC. And so Core is kind of the current version there. Database-wise, you would choose Microsoft SQL, obviously, in there because, again, Microsoft. You would also find in there something called Entity Framework. Which is what we call an ORM, Object Relational Mapper. And so the point of that was to translate between SQL and the world of C# and objects. That's what an ORM does. It helps you write code in C#, basically and translate into SQL so you don't have to write the SQL directly. Okay, and so in there, Entity Framework would use something we learned about called LINQ. LINQ is kind of a query syntax that's built into C# itself. You can use it with databases, but you can also use it with other data structures like arrays and such. You can do LINQ queries actually on arrays and other objects. Okay. But it's kind of SQL-like-ish. Okay? It works really well with Entity Framework. Everybody kind of following that? So this is still like one of those popular technologies. This is actually what we were teaching previously. As far as my own history, over on the LAMP stack, that's where I started learning most of my web development, is using the LAMP stack. I've done some stuff with Java and the Java stack of technologies, but this is really where I got my start in web development heavily, was in LAMP. And that's actually most of what I did through my college. My time in college, I did some PHP on the side. This is what I actually did professionally. When I got in the workforce, I was actually doing .NET and working with .NET websites, and this is what we've been teaching for the past 2-3 years. Right? This is what I've been teaching prior to last fall. Okay, so that's kind of what I'm familiar with, and so recently, right, just this last year, we decided to, in 2020, we made a change and we made a shift to another technology stack. Okay, so everybody okay if I erase what's there? Okay. So here's where we're going. So here's the next stack, and here's where we're going this semester. So what we've pivoted to, and what you're going to learn this semester, is called the MERN stack. Okay, you're going to be learning the MERN stack. Okay, so it's a well-known group of technologies, just like LAMP, right? LAMP is a set of technologies that they work together. They're designed to work together. Okay, you got .NET. Well, they're all made by Microsoft, so they're designed to work together. Okay, so there's a reason that these technologies were chosen, namely that they work well together, and a lot of companies are using them in combination. We, as writing curriculum's hard. Figuring out what to teach you guys and keep up with the industry is really, really hard. Okay, making that decision is really hard. Inherently, it means that we have to say, what is the most valuable thing for you to learn today? And sometimes that means we have to sacrifice, teaching this instead of teaching something else. And so that meant that we're teaching this semester now instead of teaching .NET and instead of teaching PHP and WordPress. Okay. So there's a lot of decisions that got to go in there. Whether or not we were right, that's a much more subjective question, right? It's really hard to know what is the right thing to teach, but this is what we're doing. So MERN stands for MongoDB, Express, React, and Node. Okay. So there's a few reasons for the shift. So part of the shift is there's actually a lot of things happening in the software industry right now. This has very much become the de facto standard for a large majority of the development community. It's a little bit hard because, yes, there are companies around St. Louis that have told us this, but there's also a lot of companies around St. Louis that haven't gotten to this yet. They're still using one of the previous tool sets. So, take this with a grain of salt, right? Understand that part of us shifting here is trying to get ahead of the curve and trying to get ahead of things that are happening and have already happened in the past 10 years in order to kind of make sure that we're teaching the right thing. And so this is kind of an evolution. Okay. One of the things to understand, so the key technology in here, Node, which is what this course is about, Node came out in 2010. Okay, so it's about a 10-year-old technology. It's taken a little bit of time to gain traction. There's been people that have been using it for 10 years, but if you talk to most the average developer out there, it's very likely that a lot of senior developers have never used a lot of new technologies involved. It's still pretty new. So old dogs you're talking about, they're thinking with this kind of perspective, and so you're going to see a lot of stuff even just when you're reading online. There's kind of some assumptions baked in because people are familiar with the technologies that they use. Okay? It's actually one of the reasons we're still teaching MySQL. One of the reasons we're still spending some time there is so you have that background, so that you have a little bit more flexibility in terms of what jobs you can go into and what you understand, and so kind of having that fundamentals of databases walking into here. Okay, Mongo's a little bit different, but there are a lot of things that apply across the way between SQL databases, relational databases, and non-relational databases. So there are some skills that we'll apply across there. One of the weird things that we're going to drop is the SQL language itself. Okay, so there is a kind of a language that Mongo uses, but it's a little bit different. Okay, so if we're talking about the MERN stack, so MERN, just to explain a few of these pieces. Node is an environment to run JavaScript code. Namely, it's a way to run JavaScript code outside of the browser. Historically, what you learned in the first semester, right, was how to write JavaScript that runs inside the browser. Okay, so what's the most popular browser, by the way, out there right now? Chrome. Okay, so Node actually runs on the same JavaScript engine that's used in Chrome. Turns out, it's the same V8 engine, as we'll say. Okay, so it's actually really fast and really efficient. React is a technology that's built and maintained by Facebook, originally created by Facebook, as a competitor essentially to jQuery. Okay, so it's a different way to think about your tooling. There are, regardless of technology stack, regardless of what other choices you make, there are a lot of companies using React today, which is kind of interesting. There's a lot of companies using .NET and using React. There's a lot of companies that are potentially using LAMP and looking at React because it does some things very well, and it has some history to it now. Now, the reality, though, to really use React, you need to understand Node. So that's the other side of things. In order for us to really effectively teach you React, we need to teach you Node. And we've heard a lot of things from different students, and one thing that we've consistently heard from a lot of our students is, you guys need to know React. That's one resounding thing that we've heard. We've heard a lot of different things. There's a lot of confliction in the data, but that's what's there. Express is a kind of a library that works on top of Node, makes it easier for us to build websites with it. You can build websites strictly with Node. That's possible, entirely doable, but it's a whole lot faster and a whole lot quicker to build it with Express. So that's what we're going to be doing there. And then Mongo is our database on the back end there. Mongo works really, really well with JavaScript. You can use Mongo actually with basically any technology stack that you want to. It works with Java, it works with PHP, etc. But it works really, really well with JavaScript. Okay, it's really designed to be tightly coupled with that. And so, just like we talked about some of these other technologies, there's this case where you're using technologies that work well together. So Mongo works well with Node. So that's part of the shift too. Okay, does that help kind of explain some of the background there, so you kind of know the technologies and what's going on there? Especially as you're researching jobs, you're going to see that. You're going to see some other things, but more than likely, as you're looking at web development jobs, those are going to be the three most common sorts of things you see. The other weird thing that you see a lot of times, if I go look on job posting sites, I see actually a lot of companies looking for developers that know two of these things, which gets kind of interesting. It's like, wait, what? You expect that entry level or your mid-level developers know two completely different technology stacks that work completely separately? Yeah, actually, that's on the job requirements. So, little things to pay attention to. In terms of some of the differences here, the main reason that WordPress has persisted and the place where it applies is this is largely used by people who don't know how to code, to be blunt. This is used by a lot of companies that don't necessarily need to, where there's a lot of people that don't necessarily know a lot about code. They're trying to do most of it through sort of visual UI, right? So you're setting this up for, whether it's the, you're building it for people like that they need to maintain it. Let's say I'm building it for a restaurant. We can hand it to a restaurant and the restaurant person doesn't need to know how to code to maintain the website. That's one of the places where WordPress does still shine. It's entirely possible to build those systems with anything, but that's part of why that exists. Also, there's a certain speed to getting a new site up and running with WordPress, especially with people who have done it again and again and again. Make sense? It's part of why that shines. .NET, I really think the only reason that .NET exists is because people like Microsoft, to be honest. I think that in terms of things are concerned, and having spent so many years in .NET, there are a lot of problems with the technologies that they produced and that I've personally experienced, both in terms of performance and speed and things. And if I was going to choose to build something today, I wouldn't choose .NET personally. But I know that there are a lot of companies that have a vested interest in it. Cool. They are getting better. They are developing. They are making enhancements. They've made a lot of iterations, whereas PHP's been kind of stagnant, relatively stagnant because of that. Okay. Over on the .NET side, over on the MERN side, we come back to the question of like, hey, open source. This whole thing, basically you can host one of these websites for free. The only thing in there that's not free, that's not open source, is your Mongo. Mongo has a free hosting. You can host it for free. You can get software, but there's a charge to that, if that makes sense. Long term, it's not that much if you think about how much it costs to pay your developers in that context. So there is the side of actually MERN does benefit from the free, the quick startup that LAMP used to kind of have the benefit, the market on. The other thing that this does, actually MERN's the best one in terms of scalability. If you want to build a website that handles lots of customers at once, lots of data, MERN's got some of the best tools today. In terms of handling things, especially when we talk about asynchronous coding. And that's a really big deal now to handle the hardware efficiently. Okay, questions? Does that kind of explain some of like the choices in curriculum and kind of where we're going? Just kind of weird, it's been a really hard thing for me to decide, how much MySQL do we do, how much MySQL do we don't do. And last fall, the way I played this was I said, well, we'll do the first half of the class in MySQL and talk about Node, and then midway we'll switch it over to Mongo. And what I found out and what I experienced from my own students is that they really, really liked working with Mongo in that second semester, and it was really effective. And doing the switch was that late was not as effective, created some issues. So that's why I've decided to move the shift earlier in the semester rather than midway in the semester. Make sense? So that's part of where that comes in. Okay, so let's talk about Mongo. So Mongo is specifically what we call a NoSQL database. You read through the homework. The homework was called, what is NoSQL? So it gave you some of the background behind Mongo and NoSQL and the shift. And I will say that some of the stuff on these slides, I'm going to repeat a little bit of that information, especially in terms of giving us the opportunity to talk about it. So before I get too deep into what Mongo is and how it works and some of the differences and problems and all these kind of things, what I want to start with is just kind of giving you a tease about what things look like in storing things in relational databases versus how they look in a NoSQL database. Okay, so let's talk about this example, we're going to talk about storing orders in a database. Okay, so let's say I've got this, an online store, right? You've got products that you can buy, and you can fill out orders, and so every order can have multiple products that you're ordering. So if I'm modeling this in a relational database, I might have, an orders table, a products table, and an order items table. That makes sense? So products stores like, here's all the products that we have in our store, and here's what each of them cost, and here's the name and their description and the photos that go with it. Okay, so all that information's over here. Over on the order side, here's what my schema looks like. So it's got an order ID, it's got a customer ID, so it says which customer does it go with, what date did they make the order, when did they pay for it. So it's kind of a simplified example. Okay, so it's kind of how the data is architected. Does that kind of make sense? We got an order record represents a single order. For each order, you can put multiple things into that order. So I can have, like, here I want to get one of product 1. Order 1 also has 4 of product 2 and 3 of product 3. Okay, makes sense so far? So if I was to look at this kind of on the UI, I might go look at an order, and I would see it have 3 lines or 3 items. Okay? And it'd say, here's the product you're getting, and how many of you're getting it, and this cost, yada, yada, yada. Right, so actually, as it turns out, anytime I want to look at an order, if I want to say, show me what was in that order, has it been shipped, and all those kind of things, I basically always have to look at orders, the order items, and the products table, because none of those 3 tables have any useful information basically by themselves. Make sense? Right? All of the useful information is spread out. And so the reason it's spread out is we're trying to avoid duplicate data, right? We're trying to avoid duplicating columns, and we're also limited by the fact that you can't have arrays and nested objects. I have to break it out so that all the values are scaled. Make sense? That's my kind of limitation. So that means, even a simple thing to see what's in my order can quickly become a complex query that maybe takes a lot more effort than you would expect it to. Okay? So here's what this looks like. Here's what this looks like in the world of Mongo. I can actually model this entire order as a single object. The way that these document databases work, the way that Mongo works, is every record in the database is an object. It can contain other objects and it can contain arrays. And so what I would do, can everybody see the screen? Can you turn off some lights? Okay, let me see if I turn off some these lights. The syntax highlighted is probably the wrong color because I've got purples. Can everybody see it now? Don, Michael, can you see? All right, so if I kind of look at that structure, right, you'll see up at the top, I've got an underscore ID column, okay, or property, more like. That field is what looks like a bunch of random letters and numbers. Okay, that's what we refer to as, say, a GUID or a UUI. But underscore ID is the primary key for this object. Make sense? For this document. The order date, you then see, okay, I've got the order date, and the date that goes with that, the payment date, the customer ID also turns out to be a GUID, right? While Mongo doesn't have foreign keys formally, we often use that concept. So in this case, this customer ID is still a foreign key into basically the customer's collection, the customer's table. Make sense? So this idea of foreign keys isn't really going away. You're going to get some more tools with it, but we still use this idea of a foreign key in Mongo. Cool? So I'm still using that. What I can now do, and this is what makes it really different, is I've got an items property, And you can see it starts with a square bracket here, ends with a square bracket down here. That square bracket means that there's an array there. And what you're seeing here is a language called JSON, JavaScript Object Notation. Okay, it's actually borrowed from JavaScript. So that means there's an array of items. The curly braces here represent an object, which you can see the overarching thing. This whole document is an object, but this array of items also contains objects. Right? So within items, I've got object, object, object. Right? So we can see that array's got 3 objects in it. If we drill in a little bit deeper, I'll see, okay, the first thing you have in your order, there's the product ID. Product name is red leather cowboy boots. Product price is $160. You got one of those. You also have this other product, boot socks, $15, 4 of them. Belt buckle, product price, and 3 of them. The nice thing about this structure is I can literally take this entire document and show it to you directly. I don't have to make another trip to the database. I just make one trip, give me the order, and now I have all of the information in the order in one package, which is amazingly awesome.
And so, like, say you had, I'm assuming this is for like a customer, like,
Yeah.
customer ID.
Uh-huh.
I could still look up like belt buckle, but I could maybe like search everyone that has bought a belt buckle.
Yeah.
Okay.
Absolutely, I can still do that. I can still do that.
What do you mean when you say that you don't have to query the database again?
I don't have to go back and ask for what's the name of the product. I don't have to go look into the products table because I've got that information right here. Same with the price. I've got that information right here. I don't have to go make a join between the order items, and the products table. I don't have to bring 3 tables together just to get an answer. Does that make sense? Because it's all contained, self-contained in that one document. Make sense?
Makes sense.
So what this does, it makes it a lot faster to query the database. This is a really easy query to write, and literally you just say, hey, give me the one record where the ID is. That's it. It's like the easiest thing to do. So one thing to consider here, though, in order to make this happen, I've had to choose to duplicate some data. Right? In order to make this happen, I've chosen to duplicate some data. Right? So I still have basically a products table, right? And the products has got all the products and their names and their descriptions and their prices. Can everybody see where the data is duplicated? Product name and product price. That is duplicate data. Okay, clear with that? So what we call that, and we actually use that oftentimes with relational databases today as well for performance reason and for other reasons. We call that denormalization. Okay, so normalization is the process of massaging your schemas to the point where you have no duplicate data, where all the data is there's one source of truth, it's only stored here and nowhere else. Okay. What normalization accomplishes is it means that you don't have a lot of redundancy. You can store it in the least amount of storage space as possible, and that if you make an update, all the data will be consistent and correct. Tracking with me? So that's kind of the benefit of normalization. The downside of normalization is that it makes your system slower. Because it means that anytime I want to go grab a piece of information, oftentimes I have to run a more complicated query to go get it from somewhere else. And I think you guys saw that with some of the labs yesterday, right? You're working through with the MySQL lab, where you say, hey, I want to go find, for some of those examples, you say with the rentals, you had to join, like you needed information from the rentals and the inventory table and the film table and the customer table, and you had to pull all that together just to do something that might seem pretty simple, right? And largely you had to bring in another table just because the name of the thing was not in the table where you started with. Does that make sense? So the down, basically the downside of normalizing your database completely is that it makes it slow specifically to query it. When I need to read data, normalized data is pretty inefficient. Make sense? It turns out that duplicating data, whether you're talking about relational database or whether you're talking about NoSQL databases, duplicating data makes it faster to read it. Comes at a trade-off. If I need to modify the data, it's now more expensive. If I have duplicated data, it does make it more expensive to modify that data. Does that make sense? So what does that mean? Well, it's very fast to read this order. Very fast and simple to read this order because of that duplicate data. But let's say I want to change the name of this product. I want to change the name of the product. If I don't go update this record, then the order may have the old name of the product. Does that make sense? If I name if the product name changes, if I want to keep it all in sync, not only now do I have to update the products table, I may also have to update the orders table, right? So I've added more work that I need to do if I potentially need to change the name of the product. Does that make sense? So denormalization can make your writes slower, but your reads faster. Okay? So that's a trade-off you have to consider. And what I find more often than not is there's a lot of cases where you're doing a lot of reads and not very many writes. Does that make sense? So for instance, if we think about the case here, let's say the product name changes. How likely is that to happen? How likely is it for the name of a product to change?
I would say it is pretty rare.
Very rare. Very, very rare. In fact, your customers will probably be angry at you if you do that because you're making it look like something is you're kind of being inauthentic. Because you're saying, okay, I'm going to change it from this name to this name. Well, but I bought the old thing, right? So, it's very rare, and it's generally not something you should actually do. You might do it early on because you put in the incorrect name, right? You might do it before you get any orders because you're kind of fleshing it out and drafting it, but once you start getting people to buy it, you probably shouldn't be changing the name of that. Does that make sense? In fact, there's been cases, if you look at Amazon, where hackers have gotten in, taken over product listings, and changed it from one product to a completely another product. And guess what? It keeps all the reviews from the previous product, which really are no longer relevant because it's a brand new product. Even if it's just, here's the 2020 model to the 2020 model, it's dishonest for the reviews to carry over.
Okay, that sounds really petty on the hacker part. Like,
So think about it this way. Let's say there's a highly rated product in there. It's got a lot of 5 stars reviews, right? Somebody gets a hold of that. They now put their own product here, and it's now got hundreds of 5-star reviews. It's not just petty, right? It's downright deceptive. Does that make sense? So it's actually a bad thing to change the name of the product. Outside of, again, once customers have started buying it, you shouldn't change it. In fact, it's safer for us to say once the customers have started buying it, I don't care if the new name has changed. I want my order to reflect the name that it was when I bought the thing. Does that make sense? I'd much rather have my order say the name of what it was called when I bought it.
Well, I was just thinking in that case, like, if they were wanting to change the name, we need to just create a new product ID and a product name.
That's the safest thing to do. That's the safest thing to do. Say, if you need to change the name, we're going to just treat it as a new product. You just build it into the database as a new product. That's the safest thing to do. You're saying?
Same price, you want the order details.
Same with price, right? Because if this product goes, you know, hey, maybe next week it costs $200 to buy the same thing, I need to keep track that my customer paid $160 and not $200. So I do want to duplicate this data because I want to keep track of how much they actually paid. Because whether there's sales, whether there's price changes, it's very likely that the price in the store is not the price that they paid, right? So duplicating data here actually is a security enhancement, basically. It's not just a performance enhancement. This really helps me from tracking and tracking and security to know what is the price that they paid and what was the name of the product at the time. Does that make sense? So that way I know, for instance, hey, they bought the 2020 model, not the 2021 model. Cool. So duplication here is not a problem, it's a benefit. In fact, it's something you should be doing even with relational databases. You should be copying some of this data. It's a good thing to duplicate data. One of the downsides with that, obviously you're using more storage space, right? If I'm duplicating data like this, I am using more storage space. But I have the option, I didn't have to duplicate this data. I could have chosen to keep the product name and the product price in the products table. That was completely my decision.
Can we just backtrack real quick? I heard you talk about duplicating data earlier,
Yeah.
and I keep mentioning it.
Yeah.
You're talking about if we had a relational database and all these things point to each other with foreign keys, and you change one aspect of the product,
yeah,
then that person's order for that product will also reflect that change.
Yeah.
So
if we don't keep track of what the original name was, right? If I don't take if I take the schema that I have here, notice that I don't have the product name and the product price in here. So if I follow the schema, I have no idea what the name of the product or the price of the product was at the time they bought it. So they could buy it on sale at $100 and return it and turn it when it goes up to $200, and I would need to pay them $100 for them to return it. I'd be paying them an extra $100, giving them back $200 when they only spent $100. So even here, I should still be duplicating that. Does that make sense? That's one of the things that people often miss in the shift between Mongo, say a relational and a non-relational database. They think, well, I shouldn't be duplicating data. There's no purpose. I should always be trying to avoid duplicating data. But there actually are a bunch of cases, even relational databases, where you should be duplicating data. Because like we're talking about here, security, tracking, making sure that you know what's actually happening, all of those kind of things, as well as just a performance standpoint. Because duplicating the product name also makes queries here faster in the SQL world, because you don't need to join in the products table, right? If I duplicate that data, I can get what contents are in the order without having to join in products. Make sense? So duplicating data is actually not the main thing that we're concerned with in terms of writing databases today. That's one of the takeaways. Okay? That's one of the takeaways. Is that used to be one of the key reasons why we went to the database, why we were designing databases. It used to be our main goal was to reduce duplication. So I think you saw that in some of the early articles, right? And CBT nuggets videos and such. That's not our main goal anymore. Okay? So what are our main goals? We're actually more concerned about things like security and fraud, because it's a prevalent thing. Like, those are more important. And speed. Speed is really important today. When we're talking about old systems, people recognize the internet's slow, and so it's going to take some time to do things. And so it's like, well, if it takes a few seconds for a page to load, no big deal, because it's going to take me 30 seconds to load that darn image, right? Load the product image. So who cares if it takes 3 seconds to do the database transaction? Well, now our networks and other things are so fast our actual bottleneck with a lot of real-world applications is the database. It used to be the internet speeds that was our main bottleneck. Now it's the database that's our main bottleneck. Does that make sense? So our priorities have changed a little bit. That's the other thing to kind of understand. So it's more important that the database is fast, especially because your users are expecting, you know, lightning fast turnaround, right? They're expecting they click a button to go to another page and the page is like immediately there. They don't want to wait 5 seconds for it to load. So that's more important, right? We look at the second order, it would look like this. Main difference being that it's got 2 items there. So this is kind of that's the difference between looking at it in a relational database side versus, hey, if I've got nested data, this is how I'm going to design it. And so you can see that like the design choices are very different, right? It allows us to nest data, but the kinds of things that we talk about and the reason that we do things are totally different than what we used to talk about. Does that make sense? The kind of things we care about have changed. And so that's part of what's leading this shift. Okay, so what is NoSQL? And this is kind of leading back into the article that you read. And I'm going to pull some quotes from it. So when people are talking about NoSQL, when we use the term NoSQL database, we typically use it to refer to something that is a non-relational database. It could be that that database is using SQL. It might not be using SQL. But the fact that it's not built in a relational sort of model is really what we're talking about. The term NoSQL is not a great term, to be honest. Like the term we should be using is non-relational. But NoSQL is the term that really has taken over in the industry, and it's the term that's most commonly used. But really the way to think about it is what we mean is non-relational. So for instance, Couchbase is in a lot of ways very similar to Mongo. It's a more complicated database, but it does understand SQL. With Couchbase, you have sort of a MongoDB database sort of model, a non-relational model, but it actually does understand a version of SQL. Does that make sense? So there are some non-relational database out there that do understand SQL. Okay, just to muddy the waters a little bit. So that's why this can easily get very confusing. So either way, what we mean is that what we're agreeing on is when we say NoSQL, is that we mean that we're storing the data not in relational tables, we're storing it some other way. Does that make sense? The key takeaway that what we mean when we talk about no relational is we mean that we're not using tables. We're using some other model. Another thing to understand about NoSQL databases is we're not throwing away relations. Even though we say this is not a non-relational database, doesn't mean there's not relationships. In fact, there's relationships all over the place. Okay, what we mean is we're not using the conventional way of talking about, not limited to the conventional ways of talking about relationships. So the conventional relational way of talking about relationships is you have primary keys and foreign keys, and that is the only way to model relationships. Does that make sense? In a relational database sense, every relationship has to be modeled by foreign keys and primary keys. You have no other options. So you're limited, right? That's how you have to model things. Okay. So the thing with NoSQL is we can still do those, actually. We can still use primary keys and foreign keys. And in fact, you saw that with the example. I still have a customer ID that refers to the customer's table. The trick is that's not the only way for me to model relationships. Okay? It's not the only way I can model relationships. I can model relationships now in other ways. So one of the ways that we can model relationships with NoSQL is we can model it by nesting data. We can nest documents, objects, arrays inside of other things. So, for instance, if we think about this, right, I've got a relationship with the products and the items that are in that order. There's relationships here, but I'm not using foreign keys and primary keys to keep that relationship. I'm using nesting. Make sense? So this is another way to deal with relations. You can either choose to break it up into two separate tables, two separate documents, or you can combine them into one document. In fact, it turns out with NoSQL, remember with SQL, I said the only way to deal with many-to-many relationships is to make a bridge table. Remember that? It's actually not the only option with NoSQL. It's one way you can solve the problem. With NoSQL, I can say, okay, I'll break it off into a bridge table, or I can use an array on one side or the other, or both. I can use an array to represent that many-to-many relationship. So actually, oftentimes, many-to-many relationships are a heck of a lot easier to deal with in a Mongo database because you have different ways to do it. Catch is you have to figure out which way is the right way for your particular application. And it's not as easy as saying, well, I only have one choice, it's a bridge table. Well, no, you've got like 3 or 4 different choices when you're dealing with many relationships. So you have to kind of understand your data a little bit more. Cool? Make sense? So relationships aren't going away, and you can have NoSQL databases that use SQL, which gets really confusing because you can, neither of those terms really make any sense. It's like it's non-relational, it's not SQL. Yeah, and I think this is what took me a long time to, this kind of confusion took me a long time to jump on the NoSQL bandwagon to try it out myself, really understand what people are talking about. Because like, well, SQL is such a great technology. Why would I want to get rid of relationships? How am I going to model my data if I don't have relationships? The answer is the terminology is just bad. It's misleading. It's in a lot of ways incorrect. So I don't know what what would have been a better term for us to use in terms of talking about these as an industry. Whether we're talking about non-relational or whether we're talking about NoSQL, but NoSQL is the term that's kind of won out. Okay. So where did these things come from? So NoSQL database kind of started emerging in the late 2000s as you saw a drop in storage space. As there were changes happening with how storage occurred, as we saw the growth of the internet, as we saw a lot of different things happening, we kind of saw a shift, and one of the important shifts that we saw is previously, like, storage was really expensive, okay? And the hardware was really expensive. And so the cost of your developers was a minor thing, right? It wasn't that expensive to hire the developers to work on the software and to work on the databases. Does that make sense? So our goal was to optimize the thing that was expensive. Well, the thing that's expensive today is your developers. Okay. There's an interview had an interview just this morning with a Rankin alum that's working at Daughtry. Does anybody know what the entry level salary is for junior developers starting at Daughtry?
My guess would be around $55,000.
It used to be. Actually, it used to be a few years ago. It's gone up. So entry level salary at Daughtry is $70,000. Not the only company that's at that price range. So you talk about entry level developers, $70,000 a year, up to like experienced developers, which are over $100,000 a year. What's the most expensive thing? Your salary, your developers, right? Your developers are the biggest cost in software development today. You can buy a software developer a laptop and 3 monitors, and that's still in a drop in the bucket compared to how much it costs to pay them. Does that make sense? You know, the cost of hosting the database, the cost of the hard drives and the things that go into there are trivial compared to how much time it costs, how much money it costs to pay you to do the work. Does that make sense? So it turns out, actually, the best way to save money is to reduce how much work your developer has to have to do. Rather than optimizing the hardware, which used to be the key thing, we want to optimize the work that we have to do. Does that make sense? Which is kind of weird and is not something that people are familiar with, especially getting into the IT industry. I don't know that everybody's understood that yet. But the most expensive thing now is your developers, which means that we care a little bit less about optimizing hardware than we used to. Does that make sense? Like the key thing, if you look at your average computer science program, the average computer science program, that's what we're focused on, optimizing performance, optimizing the speed and the time it takes to do things and the amount of memory we use. But memory's cheap. Processors are cheap. Servers are cheap. Even electricity is relatively cheap compared to, you know, that giant salary that you're paying. So developer productivity is really, really important. Now to kind of illustrate this, this was the graph that was on this article, and I'm kind of throwing some other things next to it so you can see. And when we're talking about, you know, back in the 1960s, 1970s, remember this is where databases, relational databases originated, right? Back in this space. How much did storage cost per megabyte back then?
1,000.
Look at that top number. $6,000 per megabyte of storage. $6,000 per megabyte of storage. Obviously, because it's that expensive, we can't have very much storage. Right? We can't. Your company can't afford to have very much storage. So you have to get the most bang for your buck out of that storage. Does that make sense?
According to the graph, it was more expensive. It was more expensive in the mid-70s than it was in the 50s.
Yeah, there's some kind of weird oddities coming through with this graph. It's like, yeah, it almost looks like there's a drop here and then a peak. I think part of that may be honestly due to inflation in that. I don't know exactly what that anomaly is. I think part of that may be due to inflation. Okay. So there's some kind of noise happening there. And then when we get going further, we see a drastic drop, you know, starting around 1980 and going down to today, we see a drastic drop in what it costs. Right, so today we're down here. It doesn't even cost a cent per megabyte. Right, this is a fraction of a cent. You see that? Tiny fraction of a cent per megabyte. So it actually doesn't really matter that much. You know, saving space and storage is not that important. Like I talked about duplicating data, like duplicating the product name and the product price. Duplicate it. It's much better for you to know what they bought and be able to query the database faster than reducing how much storage space you use. Does that make sense? We also see the growth of things like, you've heard maybe the term big data, right? You think about how Facebook operates, right? What's Facebook's key market? How do they make money? Advertisements. How do they make money from advertisements? Sell it to the advertiser, right? So the reason that people want to buy ads on Facebook is because you have all these eyeballs and they have all this data on you, right? In fact, turns out it's in Facebook's best interest to keep every little shred of data that they can, because they can turn around and make money from it. Make sense? So for these large companies, it's really important to keep all of the data, even if it turns out, you know, it turns out it's better to keep the data, even if it turns out that we can't make money off of it. the chance that we could make some money off of it is reason enough to keep it. Does that make sense?
So what data is it possible to potentially make more money off of it? That there's no time to save it.
Yeah, so that's a complicated thing. But recognize, how much does it cost for you to use Facebook?
Free.
It's free, right? It's free. Turns out that's because your data is the product that they're selling.
That's scary to think about.
Right? You as a Facebook user, you are the product, you're not the customer. They're not making Facebook for you, they're making it for the advertisers. And whoever else they might want to sell the data to, which just happens.
Okay, that last part sounds really, really ominous. Could you elaborate a little on that so if do anything or update?
What I mean is there's a story, what was the name of the company? But just last year, I think it was either 2019 or 2020, where they actually sold data to another company. They actually just straight up sold the data out. It's like, here's a dump of some of our data. Does anybody remember the name of that? I forget what the name of it was.
Is that brought on the Congress floor, or was that the separate?
It's one of, I think that was one of the, I think that was part of it.
I would just say, like, in terms of that, like, the problem is when you, like, create an account, like, you accept
Yeah.
your agreement. So whatever is within that agreement, you consent to. So if it's going to say in that agreement, then basically they're collecting your data.
Yeah, and as it turns out, that's pretty much every website on the internet right now. Is that you're signing an agreement saying they can do whatever you want with the data. Historically, the argument has been, I think the argument that people have made is like, well, then just don't sign the agreement, right? But that's a harder, to make when every company does it. There's not really a company that you can go out there and say, hey, I want to sign up for this, and I don't agree to get rid of my data. So I think what's actually, the trend actually, has everybody heard about GDPR? General Data Protection Act? Read it. Take a chance to do some research on GDPR. Make a note make a note about that. Definitely go read up on what GDPR is. It's a EU-based set of laws, came out several years ago. It commonly is known as the cookie law, but it's a lot more broad than that. And if you're building anything for any websites that might potentially be used in the EU, you need to know GDPR like you're from front to back. You really need to know about some of those laws. So the upside of that is it's actually put into place a bunch of protections and a bunch of rights to European citizens, where they have been able to, because of that, it said, no, that data is not really owned by the company, it's owned by the citizen. And so that's what we're potentially seeing, a reversal, is the governments are getting together and saying, no, here's some rights that our citizens have. You've got to give them these things, you've got to do these things. And so that's the shift. Does that make sense? So some of those things that used to be basically a wild, wild west, you sign the agreement, it's done, doesn't apply to European citizens anymore. Okay. There's a number of things in those terms of services that don't apply if you're in the EU. Some other countries have followed suit as well. Okay?
Well, just going back to like the price of data.
Yeah.
With it dropping so much.
Yeah.
To new devices that come out with obviously like the induction drive.
Yeah.
Is that price more factored on like the speed it can like transfer and write data, or is it because like I mean obviously it's still cheaper.
Here we're just talking about capacity. Like the only thing on this thing is we're saying capacity versus time. The cost of that capacity versus time. There is a question, you're right, there's a question of speed, and it's also gotten faster. That also has changed, but this doesn't say anything about the speed, okay? That would be a completely different chart, and I don't have that chart. Cool? So, yes, it's gotten faster to read data, especially when we're talking about this shift from we talk from going from tape drives to magnetic disks to SSDs to M.2s. There's a huge shift, and things are much faster than they used to be, okay? But they're also just price per bit, price per megabyte has gone drastically down. Does that make sense? So that's one of those things to consider, and you have to kind of realize that's there. I was saying something before class started here, and I kind of mentioned it on perusal on the discussion. There's another thing in here that's kind of worth pointing out that I wanted to bring up in terms of this. So one thing to notice here, you see this is $6,000 per megabyte. Okay, so there's pretty crazy stuff going on here. When we sent astronauts to the moon, okay, we actually send it with very different memory that you probably have never seen or heard of, okay? So the kind of memory that the Apollo missions used is something called core memory, okay? And if you look here, this is this module here, this kind of cubicle module. That's a core memory module. That's the kind of thing that we used to send astronauts to memory. If I remember right, I think that was less than a minute, that block. Okay. So the way that that's put together, you kind of see a picture of the weave. It looks almost like this is woven. This is what's actually in there on each of those faces, is this weave. The way this worked, it's actually really interesting. So you had wires like this going in a grid. Okay. And so you run electrical signals through these. So you say run an electrical signal through this wire and that wire, and so you'd be kind of electrifying intersection. At each of these intersections, we have these little iron rings, which are magnetized. So they could be magnetized one way or the other, and that's where you would know if the bit is on or off. It's in north or south polarization, right? And so what you could do is you could run electricity through to the intersection. That would flip that one bit, and that's actually what they used to go to the moon. Okay. Now this was so small and tiny, and if you look at it, it looks almost like it was woven fabric or that kind of thing, right? So these were actually woven by seamstresses. So you look at this person, she's actually using a needle and wire to make these things. That's the kind of work that went into making memory in the 60s and 70s for the Apollo missions. You see that? I think maybe you can understand, right? That's a lot of work. That's why it costs so much to make a single megabyte of memory, because that's not an easy thing to do. Cool. That's the other thing that's shifted is, the amount of work it costs for us to make memory back in the day was just astronomically huge compared to what it is today. Today it's like, there's like hundreds or thousands and millions of these chips being made every day in the factory, basically by robots. Right? There's hardly any human interaction today when you make memory. There's some human interaction that's designing there's a few engineers that design the circuit boards before they go in, and there's some people that do QA at the end. All that work in between is just machines, right? And so things are much cheaper than they used to be. Make sense? So that's one of those things. It's really all that points to is, hey, there's been a huge shift, and the thing that's, storage space, which used to be really, really important, is not as important as it used to be. That used to be one of the reasons that we had to do all this relational database stuff, is we had to try and get it down to the smallest amount of storage space as possible because it was so expensive, right? Mongo is still pretty efficient, so it's not a huge waste of memory, but it just means that that's not the thing that we're most concerned about. Does that make sense? And also why I said, hey, just use a bigger integer. Okay? If you want to use your primary keys, just go ahead and use big int, because the difference in memory is really inconsequential at this point. With a relational database historically, you've got these varchars and these cars. The whole point of the varchar having a limit is you're trying to limit how much space that string takes up, right? And so you can say, hey, well, my longest string is 10 characters, so I'll make it a varchar 10. Or maybe I can squeeze it down further. I'll do like varchar 5. And then things that would happen probably is like, well, let's use these really complicated short ways to shorten names and things like that. Like, okay, we'll make the usernames, we'll limit usernames to 6 characters so that I can fit in less data storage. Like, that was a normal thing in the 60s and 70s. They say, hey, well, usernames, we're just going to say you only get 6 letters in your username because otherwise it would take up too much space. You don't get to, like today, you can basically, hey, you want a 30-character username? By all means, go for it. You don't even think about it, right? Whereas that used to be much tighter than it used to be. And so if you look at old stories, you see a lot of old stories of schools trying to go through these complicated schemes to come up with 6-letter usernames for all of their staff and faculty and things. It's like, okay. So we don't do some of that stuff anymore. So some other things that happened, we started seeing, as these, in 2000, we started seeing this rise of data that came in that was less structured, semi-structured, and sometimes it was completely unstructured. Completely unstructured, that's a thing that we started to need to handle more, including this idea of like polymorphic data. If you think about your second semester class when you're doing C#, remember hearing that term polymorphism at some point? Polymorphism, where you can kind of treat an object as the same thing, treat it similarly, even though it may have maybe a different class, maybe it has different properties, maybe it has different methods, but the way that you kind of did polymorphism is you had a common base class, if that makes sense. You can actually sometimes you find that you need to do that when you're working with your data, right? So maybe you have some users in your system. Let's talk about a school, for instance. You have students, you have faculty, you have staff, right? The information that you keep about those different kinds of users might well be different. I might well want to keep different data about students and different data about instructors and different data about staff, right? But with a relational database, I have to squeeze all those things in to the same columns, right? That's a problem. How do I say, well, for instance, maybe instructors, I don't want to keep their date of birth, but I do need to keep, like, how many courses have they been taught? What was the day that they started teaching? What was their master's or the bachelor's degree in? I might want to keep that information. Versus if I'm storing students, I need to keep track of their GPA, maybe their date of birth, and the kind of schema and the requirements for a student object is very different from an instructor object, is very different from a staff sort of person. The other gotcha, though, is what about so one thing you might say, well, we'll just split those up, and we'll say, here's an instructors table, and here's a staff table, and here is a students table. Okay, well, there's 2 problems with doing it. First of all, now I have, now if I need to write code that works with any of those, I may find myself writing a lot of duplicated code. because I have to write it to work with this table, write it to work with this table, write it to work with this table. So for instance, hey, maybe all three of them have an address. Well, now I've got to write an address form that works for this, the address form that works with this, and the address form that works with this if they want to change their address. And they're 3 copies of the same code. That's a problem, right? And it makes my queries a lot more complicated too, because now it's like, well, which one do I go to? It gets worse. Well, what if you have somebody who is both staff and a student? Let's say they come on as a teacher's assistant or a student worker. Now they're in the staff table, but they're also in the student table. So commonly what we'd like to do is we want to say, well, here's a users table that is everybody that can log in and can be part of the system. Does that make sense? But it often turns out that those users have different kinds of data based on what their role is. Make sense? So that's one of those places where you start to see polymorphic data is in cases just as simple as that, where you're dealing with users that have different roles. Make sense? So that's, those are things that happen there. You're also dealing with data that's coming from other sources, like if you're dealing with advertisers and those tend to have, this company has their data, this company has their data, this company has their data, and maybe they don't want to agree on a common schema. We have to make something that works with that. Or maybe we want to build something like a blog. And so this person wants to set up their website and all their blogs have these attributes. This person wants to set up their website and their blogs have these attributes. And another person wants a different blog. Or let's say you're making an e-commerce platform. And so somebody wants to build a shop that sells t-shirts. Somebody wants to build a shop that sells computer parts. Somebody wants to build a shop that sells plants, right? Well, they're going to have different attributes, right? So the person who's trying to sell plants, well, their shop, they want to know things like what season should I plant it in, how much water does it need, how much sun does it need. So they're going to want different rows and columns. They're going to want different columns and fields on their products. Does that make sense? Their attributes are going to have way different proper products. If you're dealing with somebody who's selling PC parts, right? You want to know, hey, I want to know the CPU frequency of this part and how much memory capacity is on this memory module, and how much power output does this graphics card need? And so every part's kind of got its own attributes, right? But they're also different than what the person selling plants wants. Or if you're selling t-shirts, well, I need a t-shirt size. Like small, medium, large, extra large. But those attributes would make no sense for these other kinds of stores, right? So by actually allowing things to have less structure, you can end up building software that works for more people. Does that make sense? I can build a baseline. If the schema is more flexible, I can build an application, a baseline of a store that works for everybody. And I just say, well, these people will have some additional columns that other people don't have. And especially in the PC part space, that's especially helpful because different types of parts have different attributes. Does that make sense? I'm not going to look for the same specs on a hard drive as a memory module and a CPU and those kind of things. They'll all be different. So that's really, really helpful, right? It's really helpful for storing and dealing with those things. Cool. So that's, we have a lot of problems that we're trying to solve that we weren't trying to solve originally. A lot of things that we weren't doing. Another thing that's happened in recent years is we started kind of pursuing something called Agile. Okay? Show of hands, anybody heard the term Agile? You heard about Scrum. Anybody heard the term Scrum? Anybody heard the term waterfall? Okay. So, this is something you should know. Okay? So, there's two kind of, at least in theory, programming camps. There's the waterfall sort of programming camp where you say, let's define and figure out all the requirements. We'll write down all the, waterfall says, write down all the requirements. Let's document all of that. Let's create a design and plan the entire system out. We'll build it. We'll test it. We'll QA it. We'll find all the bugs. We'll fix them. And then we'll release it to our customers. And we're done. Think of it like building a car, right? Which building a car kind of follows that, or building a house follows that method, right? I don't want to, if I'm building a house, I can't come here in the middle while I'm building a house and say, oops, I didn't set this beam up in the right place so it could be load bearing. Because I get down here and I'm testing it and the whole house falls down. That's a problem, right? So when you're building houses, you have to follow this waterfall model. You have to plan it all the way up the end. You have to figure out what all the requirements are, what all the forces are, where every piece is going to go before you start sending anybody to the workforce. Before you lay the concrete, you have to know the entire plans for the house. You can't start building the house until you know everything beforehand. Same thing happens with cars, right? You basically need to design the entire car before it goes to the production line. Does that make sense? Fortunately, and so originally there was some theory and thoughts like, well, let's become more engineering. Let's be more like these other engineers. And so these other engineers, in architecture and such, well, they do all this planning up ahead of time. So let's be like that. Let's write good software and we'll figure out all the requirements up here. We'll go build it, and I'll be happy and I'll be good. Turns out, software doesn't work like building houses. Because unlike building houses, you don't get the customer here, the person who's going to have the house, come in the middle and say, oh, I don't like that, change this. But that happens all the time when you're building software. Somebody, whether it be your customer or your boss, comes in here in the middle and says, oh, I don't like that. Do this instead. And maybe they change then you have to completely go back to the drawing board and say, okay, I'm going to have to rethink everything. And so you rip out some support beams, you do this, you add some extensions to the house, and okay, now it's here, and now it has a deck where it didn't have one, and okay, well, you want the washing machine or you want the air conditioning to be over here, and so I'll do all those kind of things. And so you're doing a lot of changes in the middle, right? Does that make sense? Adapting to changes as the requirements change. And it turns out in software, it's impractical to know all the requirements ahead of time. There basically are no real projects in writing software where you know everything before you start. It's not possible. And even if you could, software is a rapidly evolving space, right? So what works today might not work in a year or two. There's constantly technologies happening with the web browsers, with HTML and CSS and JavaScript and all of these technologies, so that by the time you get it built, the technology and the hardware is shifted. So what might have been a good design back then, it might have met the requirements and the needs that they wanted. 2 years later, when you finish the project, you're not building what they want. Does that make sense? So we have to, as an industry, be able to evolve and adapt to changes in hardware, changes in software, changes in requirements as we're building it. That makes sense? So this is where this term agile comes in. Okay. Let's see, is there a year on here? 2001. Okay. So in 2001, a group of kind of senior developers got together. They had seen some of the problems with what they were trying to do and said, hey, we've got some thoughts. We're going to put them down on paper, and maybe it will help to make the software industry better. Okay? Because we're finding out that the way that we've been doing software maybe isn't practical. Okay? Maybe it isn't practical to know all the requirements ahead of time and do things we're doing. So here is the Agile Manifesto, written in 2001. So let me read it to you. We are uncovering better ways of developing software by doing it, helping others do it, and through this work we have come to value A over B. So there's a few different lines in here, okay, and basically what this says is this thing today is more important than the other thing on the right. It doesn't say that we're exclusively going to do the thing on the left and forget about the thing on the right, which sometimes happens. It means we're going to do a little bit of both, but focus more on the thing on the left. Okay? So first one would be in individuals and interactions over processes and tools. So historically it's been, we need to follow the process and use certain tools, and that's the most important thing. If we do that, we're going to build good software. What we said is like, well, actually what matters more is how we work with the people that we're dealing with. How do you work with your customer? How do you deal with the stakeholders, the people that are giving you the requirement, the people that are actually going to use the software, the people that are paying you to make the software? Let's value the interactions and or work with them over strictly following a process. So that means that we might set a process, and this is saying, hey, this is normally we do these steps, but we're going to make exceptions and favor, what's better for that situation. Rather than strictly saying we have to do this and we have to do that. Next up, we're going to say we favor working software over having comprehensive documentation. We're going to favor having software that works and demonstrates and works the way that the customer wants, and not so much having a giant 200-page manual that tells you every little detail of that program. Does that make sense? It's actually what we used to do. In fact, if you look at old video games, how big were those manuals that you got with those old video games, especially computer games? I've got an old computer game, and the book for it is that thick. I kid you not. It's got like 100 pages. Right? But you don't see that anymore. You buy a game from, say, GameStop, for your Xbox or your PlayStation or whatever, and maybe there's like a one-page handout that's like an advertisement inside of the sleeve, right? All of the instructions, if there are any instructions, are actually in the game. Like press this, press A, or press X, or press circle to jump or to attack or whatever it is. All that instructions have moved into the game or the software itself, rather than being separate in a giant manual that you would have to read through. Does that make sense? So we've seen that shift. That's part of, this agile is part of what's led to that shift. It's not the only thing, but that's been part of that shift. So it doesn't mean that we necessarily throw all of our documentation away. There are still plenty of great reasons to have documentation, especially if you want to bring new developers on board. It's good to have a certain amount of documentation so that they know how the system works and so they can effectively write software. But it means that writing a 100-page manual maybe isn't the most important use of our time anymore. Okay? So that used to be the norm. That used to be the norm where part of your work as a developer is to write a lot of documentation about what you wrote. Is to write all that paper. Next up, we talk about customer collaboration. This kind of fits into the individuals and interactions. We're going to focus on collaborating with our customers and building the software that they want, rather than negotiating the contract, rather than writing the contract in such a way that, historically say, we're going to write it such a way so you can't get out of it and we can't get out of it, and locking ourselves in that way so that we can't make changes, right? We're going to say, hey, up front, we're going to agree on this is what we're building, or how we're building it. If you don't like that, if you change your mind, tough luck, this is the contract. What we've said, well, no, we're going to collaborate with you. We're going to keep asking you what you want as the process goes on, so we're delivering what you want. And that may mean that the product, we initially set a budget, and the budget's different when we might go over budget, we might go under budget. We'll charge for how much it ends up costing to build that thing, right? But we're going to focus on building the thing that you want. Make sense? Okay. And same like here, we want to focus on responding to change when change happens, whether it's in the hardware or the software or the customer or whatever else, we're going to focus on doing the right thing given those changes, the things that have occurred, rather than strictly saying, we planned up ahead of time, this is what we're going to do, so we're going to stick to that plan. We're going to change it as we need to. Make sense? So that's kind of what this Agile Manifesto really set the groundwork for Agile development, right? It's a good term to kind of understand Agile development is something called iterative. We build a version of the software, we show it to our customers, we get some feedback. We enhance it, we show it to our customers, we get some feedback. We do some more work to it, we show it to our customers, we get some feedback. We keep adding on to it, okay? We keep doing this feedback loop. And so that's really what Agile is about. There's a lot of different ways to do Agile. There's a lot of different kind of processes that you can follow. Kanban and Scrum are the two ones that you hear most commonly. A Scrum is typically like a 2-week iteration cycle where you go and you make some plans and about what you're going to build. You go away, you program for 2 weeks. You come back and you show it to your clients. You plan again, go program for 2 weeks, and you just repeat that cycle until you're done. But it means that rather than traditionally what we would done, we say, here we're going to make all the plans, and here's our timeline. It's going to take 2 years. We'll come back to you in 2 years, and that's the next time you talk to your customer. Basically, that was the historic idea. You didn't talk with your customer in between. But now we do it every 2 weeks. Cool. Do you have a hand up? Okay. Does that kind of make sense where Agile fits in there? So that means that we are constantly iterating, constantly trying to adapt, rather than saying we can it's not possible for us to know all the requirements, all the design up ahead of time. We'll figure it out as we go along. Cool. All right, let's take a break. So, kind of the background, the idea behind Agile. The idea behind Agile is to adapt to change. That's the whole point. Is we want to be able to ready to adapt to change as it inevitably occurs, right? No matter how long your cycle is, especially if you're working on a 2-year project, changes are going to happen. So let's be ready for them. Let's make the changes that we need it to. The issue traditionally with the relational databases is that they have that type schema, and every database environment that you're running in there has to have the same, in your software has an agreement on what that schema is. Make sense? Right? For instance, like if I think we had one of the group exercises here where I asked you to write some queries against the database and specifically get the contact info for your students. And okay, well, so several you had to make schema changes to make that happen, right? And so if I'm going to be able to run those queries that get the contact information, I need your updated schema, right? If I don't have your updated schema, I try to run your query, it fails, right? And so I comment that on a number of students because well, I don't have your schema, right? And so that becomes a problem in the workforce, right? If we update the software, right, to work with a new schema, but we don't update the schema, right, then all of a sudden we have a website that breaks, it crashes, users can't place orders, they can't search for products, whatever it is. That's a problem, right? So we have to put processes in place to keep the schemas in sync in, say, our development and our UAT environments and our production environments. That becomes difficult. It can be done, right? It can be done, but it's hard. It's especially hard when you're having your software installed on your customers' machines, which is another case we had with one of the companies that I worked with, is we actually had to, we're selling this system, they're installing and having the database on their own servers. So if we need to make a change of software, not only do we have to give them the software updates, but somehow we have to get their schemas up to date. Make sense? And that's a whole other problem, right? So that's one of the things that we've run into is how do we keep the schemas up to date in all of our environments, whether they be, just the usual dev, QA, and prod, or they be, hey, all of our customers have their own environment. Well, that's a problem, right? So that's one of the things that Mongo does really well. Mongo does really well working with cases where maybe you don't have full agreement on the schema, where it makes it easier to adapt and change the schema as you're working. Does that make sense? Because it's less strict when we're working with this. So that's one of the things that's led to a shift to NoSQL, is that it's really hard to, it makes it hard to adapt. So let's talk about some of the problems specifically with relational database. There's a few specific problems that I want to call to your attention, which is because of those problems we're going to see when we work with Mongo, that Mongo does things a little bit different. Okay. Now these are some takeaways that you can actually go back and apply back to a relational database, right? You can take these lessons and apply them back, and you'll actually make a better system even if you're still working on a relational database and not working with NoSQL. But some things you have to kind of understand. So, and we talked about some of this stuff. I talked about this earlier in the semester. I talked about this in the first week, and I talked a little bit about more today. But there's a few changes that have happened. So the kind of environment that relational databases were designed for, they're designed for a world where hardware was very expensive, both in terms of your storage and in terms of the memory. The hardware was a very expensive commodity. Make sense? That's one part. It was also designed for a place where software engineers were a lot cheaper than the hardware, right? Where the main cost was the hardware and the main cost was not the software engineers themselves. Generally, your software engineers were already seasoned employees of your company. When you got your new system, you're actually more than likely were training people in-house and getting them to work on the system, because there weren't college programs at that time to train software developers.
I wondered about that.
That initially wasn't the case when this stuff came online. So the people that you brought in more than likely had already worked for that company for 10, 20 years, and now you were teaching them how to work with your database and work with your system. And they already had a lot of business knowledge, right? So they already knew how the business operated, all the terminology, all of that kind of how that worked. And so you had a really good understanding of the kind of the company's bottom line. But when you bring a developer in now, right, you guys are going to finish up in just under a year, go out there, whatever company you land in, you're probably not going to know the first bit about their particular industry, their particular business. You're going to have to learn all the lingo. You're going to have to learn how business works. You're going to have to learn how they operate, what their procedures are, and all these kind of things. So that means you're not going to really have a good understanding of how they do business when you start to build software. Does that make sense? You come in there not knowing that. So that means you're going to make some mistakes. That means you're going to make some assumptions that are incorrect. That means you're going to have some miscommunications where you think one word means something else, means this, and this word means something else to them, right? Those are things you're going to have to deal with. But that means that it's extra hard to come up with a schema and get it correct the first time when you don't know how the business works. Does that make sense? You're gonna, not only do you have to learn and write the software on your feet, you have to learn the business on your feet. Okay, so it's much harder to just come up with the schema ahead of time. It's also worth noting at that point the internet does not exist. The point we created relational databases, there was no internet. There was not too long after that we had Ethernet cards and bulletin boards, but the internet as we know it today is a much newer concept. Got it? Hard drives also, the thing we had to optimize for was what we call sequential reads and writes. We had to make those as efficient as possible because you've got something called seek time. Seek time is how much does it take for this needle to get around to the place where it can read the data. And that actually takes time because you've got mechanical parts spinning around and this, and you have to get everything aligned and get the needle in the right place. So that in itself could take, if I want to read data here and then I want to read data over here, that's going to be slow rather than reading 2 bits of data that are right next to each other. Does that make sense? So some of the things that have happened, right, that's part of why they're written the way they are. So tables, you have the row and then the row and the row. So rows within the table are located next to each other. Does that make sense? So it's easy to read sequential rows in the table. But with our hard drives that we have today, SSDs and M.2s have really changed that. Flash memory is actually a lot faster to do random access reads. I want to read a byte here, and I want to read some bytes or some data here, and I want to jump over to completely part of the disk and read this. No problem. It's almost as fast as sequential. Sequential reads are still faster, actually, as it turns on flash memory, but it's not a huge slowdown to read data that's not sequential. Does that make sense? So that's the other thing that's changed with the hardware is random access is much faster on the drives and memory that we have today than sequential, right? Used to be. So we don't have to favor sequential reads as much. Also then, we're talking about these types of business that we were working with. Their business requirements are actually really well known and they were basically static. If you're talking about dealing with expenses, basically you can take any accounting course, it'll teach you how to do that, and it hasn't changed for 20 years. Kind of thing, right? Laws and taxes and all those kind of things have changed, but the basic way you do bookkeeping hasn't. So it's very easy to come up with requirements, make a plan, make a schema, come up with it, and you're dealing with a bank. Yeah, you know all the requirements. They're probably not going to change, right? Because of the kinds of software that we were building. Does that make sense? But the kind of software that we're building today is very different than the kind of software that we used to be building. Now, today, we're building software that's much more cutting edge, that's much more in places where we don't know the requirements for that business. We don't know for that. In fact, you may well be creating a business, a product that's never existed before, right? That it's not unusual there's a lot of products that have been built and nobody they knew they needed it until it came to market, right? TikTok just came out of nowhere. Short video clips. Who knew that it would be so popular? I mean, somebody could say that Vines came before and were basically the same thing, but, who knew, right? And so sometimes that you don't have any previous experience to draw off of, right? So you may be making a product that there's no precedent for, right? There's nothing that came before that you can say, well, let's do this. No, you make the product and then you find out how people use it and adapt. Make sense? So we're in a world where the requirements are not really static. They're not well known. They're rapidly changing. So that's what we have to deal with. So databases today, we really need to be able to handle thousands and millions of concurrent users. This is a common need for medium to large companies. So you need to be able to deal with a whole lot of concurrent users, right? You're not dealing with what we talked about in the 70s, where you're dealing with five developers that are all in the same building. They're the only people that ever have access to this database. You're dealing with 1 million people located around the globe that all need to do something with this system. Call it Facebook or Twitter, right? And so they all need to be able to access the database at the same time. That's what we say concurrently. Make sense? So that's the kind of applications that we want to build today. We want to be able to do that. We want to be able to build databases that can handle millions and billions of records. That's what we're talking about. Tables that are huge. Depending on what you're building, that may there's a lot of variability there. One of the growing industries that we're seeing is something called Internet of Things, IoT. And we're seeing that both in homes, we're seeing that in industrial automation, we're seeing that in factories, we're seeing a lot of these cases where you want to deploy sensors that can take measurements every second and ship all that data. So every second you're getting data from these sensors. And you may have a factory where you have hundreds of these sensors that are sending you data every second. That's a huge amount of data, right? But we need to be able to build applications that can handle those kind of things, that can handle those IoT industries. And suffice to say, there are some companies around town. There are a few companies in St. Louis that are actually doing IoT things. I've heard them talk a few times when we've had, we do these job fairs on the regular, and there's been a few people that have come in and talked to us at the employer breakfast after that. We've listened to what they've done. I've heard a few of them come through and talk about we need more IoT. Now they're talking from an IT perspective, right? They don't really understand that there's a software behind that you need, but IoT is a really growing thing. You see robotics, you see a lot of these things. In order to support that, we need to be able to support a lot of data coming in, more data than we might be used to, right? Because these sensors can generate data a lot faster than your customers can. Make sense? So that's one thing we need to be able to do. We also need to be able to deploy these databases in a geographically distributed way to different database servers. So let's say, a very common thing for you to do is you want your business to be able to handle international orders, international customers, which means I need to have not just one database that sits here in St. Louis. I need to have different databases spread around the globe so that there's a database that's close to them, right? You think about Netflix, the way Netflix works. Their data spread all around the globe. Their customer base is all around the globe. So they can't just have one database instance. They can't even have just 3 database instances. They need thousands and thousands of database instances to handle all the customers that they have. Make sense? So that's what we're dealing with today. And even in just small companies, disregarding the Netflix case, it's not unusual for you to have a development team that is spread around across the globe. One of the companies we worked at, we had a team here in the U.S., and we also had a team that was based out in China. Well, how do you handle those? Well, ideally you want to have them have their database instance and we have our database instance. So you don't have to constantly be traveling, sending data halfway across the globe anytime you want to do anything. Does that make sense? So that's important. Unfortunately, the way that relational databases were built, they were never designed to do that. They were never designed to be geographically separated. In fact, there are some ways with relational databases now to sync them up and create different separate database servers, different database instances. That is now possible today. There's been some work that's been done there, but it's hard and it's inefficient. In fact, it's so inefficient that it's hard to have more than 3 database instances. It's impractical, in fact. It's impractical to basically have more than 3, which is a really hard thing, right? It's really hard to cover a globe if all you have is 3 database servers. Does that make sense? If that's all practical to do. Because what happens is it grows and grows exponentially. Every database server you add has to do more and more work and slows it more and more down. So that's things that we have to be able to do. We have to be able to handle global traffic in some way, shape, or form. Okay? So, and that's one of those things that unfortunately in the relational model is not solvable. Right? Our relational model can't handle that. It can't handle that where I want to say, hey, we're going to have 100 database servers. It just can't do it. Okay? Does that make sense? Understand? This is why one of the reasons that we're talking about this now, right, is because that is a very limiting factor. And I don't think that everybody understands that yet, but it's a thing, and you're more than likely to run into it. because of the direction that things are going with globalization. Our hardware is now cheap. It's a lot cheaper than the developer hours. Our developer hours are much more expensive, so we want to optimize for developer hours and not so much worry about how expensive the hardware is. We've got SSDs, we've got flash memory, and we've got lots of RAM to work with. I mean, you can buy servers off the market now that have 32 gigs and 64 gigs. I think last time I checked, I might have seen some 128 gig server blades. So you can have a whole lot of memory in these server things. That's not a limiting factor. And all of that is really efficient if you need to do random access reads. So it doesn't matter. It doesn't matter if the data is all next to each other, which is what relational databases and tables do a really good job about encouraging you to do sequential reads. In fact, that's part of the process of optimizing relational databases. Is you want to do more sequential reads and fewer random access reads, because random access reads are expensive. That's actually what I learned to do when I was working with the database, and that's what I learned from the DBA that I was working with. He instructed me to do that, is get sequential reads, avoid the random, because that's an issue. Mongo does that a lot better. Mongo actually does deal with this, and if you're assuming random access reads are more efficient, actually there's a lot of benefit to using a database like Mongo. We're going to talk about the requirements. Again, wherever you land, more than likely the business requirements are not going to be well understood, and they're going to be poorly defined.
Why exactly are those requirements so fluid and as well as vague?
Okay, so a few things, and this is what I had kind of previously talked about, is that we've got changing technology and changing hardware, right? And so that's one part of it, is that the software and the hardware is changing. And so that can change requirements, okay? That's one source of it. The other source of it is as I said, we're building things that have never been built before. If you're building something that hasn't been built before, you can't know the requirements ahead of time. This hits especially hard if you have any interest in doing game development. No game developer ever sets out knowing the game that they're going to build. I will tell you that from experience. I'll tell that from everybody. If you're going to build a game, you do not know the game at the beginning. You maybe have some ideas, right? But where you start will be very different from where you end. Does that make sense? And a lot of software development is the same story. A lot of software development today is you start building one thing, and you think that your customers want this, and you think that the money to be made is here. And you work on it for a year or two. And over that time, you find out that the money to be made is actually completely somewhere else, and that your customers want something different than what they told you at the beginning. Does that make sense? Does that answer the question? So there's a few problems in there. It's hard to know where the money is. It's hard to know what your customers want. In fact, they usually tell you the complete opposite. They usually don't know what they want. And usually they don't know what they want until you show them. That is the reality, is they usually don't know what they want until you show them. It's like, oh, yes, that's what I want. Or I've had multiple cases where it's like, you build something for them, and then as soon as they see it, they realize, oh, I need this other thing. I need it to behave this way. And they could have never told you that until you built it, because they didn't have that in their head. Does that make sense?
So the public are fickle.
So what?
So the public are fickle.
That's one part of it. But it's also just has to do with what we're building. Does that make sense? It also just has to do with, we're not building things that are strictly tracking like finances and orders and those kind of things. Does that make sense? We're not doing things that have been done for 20 years or 100 years.
So then it's pretty common for like your first like I guess like so prototypes to be very different than the end product sometimes.
Absolutely. Absolutely. Your prototype's going to be way different than what you deliver in the end. In fact, that's part of why you make prototypes. You make 2 or 3 different prototypes. You kind of see what your customers like, and then you follow along with the ideas from those prototypes that they like much. In fact, often you might find they like an idea from this prototype, an idea from this prototype, and an idea from that prototype. And those things make it through to the final product. Make sense? Sometimes you have to show them something and then pull that out. And so because of that, these things are constantly changing because of everything. Okay, so it's not necessarily just people being fickle, I would say. It's more just like, we don't know what we want. We've never seen it before, right? We're trying to make something that's brand new, right? We're trying to make a product that's unique. So you're making a product that's unique and that's never been seen before, you're going to have some gotchas when you're trying to do that. Okay, so some specific features that I want to talk about in terms of the world of relational databases and some problems. So auto increment is actually a huge problem. Okay, it's a huge problem. It's something that I would really advise you against using. The one upside that it does is it saves on storage space because it stores the number in the smallest space possible. So it doesn't take up a lot of space. Remember what we talked about storage space? Storage space is not the most important thing to optimize. Other things are more important. So one of the things that happens with auto increment is it requires synchronization between all your database servers. If you're using an auto increment, then all of your database servers have to know what the next number is, right? So the next number is 1001. Every server in the system has to know that it's 1001, and they have to stay constantly up in sync with that. So you insert a record, all of the database servers have to be updated. You insert a record, all the database servers have to be updated. So that means, hey, I want to have 100 database servers located all across the globe. How many times does that insert have to happen? 100 times. It's going to make your insert very, very slow. Does that make sense? It doesn't scale. Okay. So it can also, we talked about this, can be easily guessed by attackers. If I know that every time I insert a record it goes up by 1, I can just try the numbers. I can say, okay, I'm going to try all the numbers from 100 to 200 and see if I can find any data and maybe find some data that I shouldn't have access to and get there. Or I might be able to guess a lot of things. So I can do a lot of trial and error and brute force attacks with these. Okay. And it also, as we talked about, reveals usage statistics. Because if I register and my user ID is 1,000, I know you probably have about 1,000 customers that registered before me. And if I register another account in a week, and my ID is 1,100, well, I know there's been about 100 people registering accounts in that week. So that tells me something. So all of that is a downside of auto increment. So Mongo doesn't support auto increment at all. It's not supported. And you don't want to use it. Okay? For those reasons, right? It would cause problems with scalability. So we're not going to use that. Another thing, foreign key constraints. So a foreign key constraint in a relational database, you're creating this idea where there's a primary key and a foreign key here, right? So number here, number here. Well, a foreign key constraint, just so we're clear, isn't that relationship. You can create a relational database and have relationships between the tables without foreign keys. Foreign keys are not required. You can choose to leave them out of your database entirely. And if you choose to leave foreign keys out entirely, you will actually have a faster database. Tracking with me? Foreign keys only slow it down. Foreign keys always make your database slower. What they do is they're trying to prevent you from having invalid data. Foreign keys exist to try and stop your data from getting invalid. but they come at the cost of making everything slow. Does that make sense? That's the trade-off. They're a trade-off between having correct data and having slow data, having slow reads and writes. So the other thing that can happen anytime you're dealing with these foreign key constraints, when you mess with data, let's say you're inserting data, you're updating data, or deleting data, it has to check both the table, like here the table that's got the primary key, and here that's got the foreign key. So just in a simple sort of relationship, if I say, let's say we have this, we've got the student, we've got the course student, and I've got over here, I've got the course, and here I've got an assignment grade. Okay, so there's foreign keys between these things. Remember that, right? Okay, so anytime, because there's a foreign key relationship here, there's foreign primary here, there's foreign primary here. Anytime I modify this course student table, I actually have to look at all four of those tables because of the primary keys. Anytime I make changes, anytime I do reads, or anytime I make writes to this table, that forces me to check all four of those tables. Because modifying this data, let's say I delete a record from here, that potentially could leave an assignment grade orphaned, which can't happen. If I modify this data here, so let's say I change the student ID, well then that might be violating this table. If I change the student ID, then I might be, hey, I have to say, hey, is that student ID valid? I also have to say, is the course ID valid? Does that make sense? So with the foreign keys, any change to this table is not just affecting one table, it's affecting four. You see the problem? Grows up pretty big as far as being a performance hog. And because it needs to do those checks, in fact, it needs to do something called a lock. Okay, a lock is a way preventing other users from modifying the data for a period of time. So it'll temporarily lock all four of these tables, at least a row or more in those tables, to do that manipulation of the data. Does that make sense? So I'm potentially having to lock four tables, or at least 4 rows, when I just want to do a write. You see how that makes everything slow? You see kind of the problem. So for that reason alone, it's actually not necessarily recommended, and especially when speed is of a concern, to use foreign key constraints. It's actually better to just say, here's the course ID, here's the student ID, and I won't actually add the foreign key constraint. Does that make sense? For correctness wise. Okay. That's actually something that's happening sometimes when people are building relational databases. Sometimes developers now will choose to leave them out because it makes things so slow. So this is one thing that MySQL doesn't support. There are no Mongo. There are no foreign key constraints in Mongo because of this performance negatives. Does that make sense? You have to enforce those and do these things yourself. Okay. There's no enforcement from the database side on these things. Okay. It's because of speed. The other thing that you get here, as soon as we start doing these foreign keys and splitting the data out, it's going to take joins to bring the data back together anytime you want to view it. That's the other thing. Can you work through that? Yeah, we did. We saw how to kind of work through that. But it requires that. Vice versa, we kind of saw with the example that I showed with orders, I can actually pull out a whole object and not need a join if I build it up that way. Does that make sense? So I actually want to avoid foreign keys to some sense, to some extent. Especially I want to avoid the constraints, right? I'm okay with using the concept of having here's a primary key and here's a foreign key, but I will want to avoid the tight constraint that causes the slowdown. Make sense? That thing, the slowdown there, is really a big deal when you're dealing with a lot of users. It can be really significant. Another thing worth noting with your typical relational database, notice that I said all the values have to be scalar, right? All the values have to be scalar. So I can't have nested documents, I can't have nested arrays. So if I want to have a blog that has articles, well, I have to create a whole nother table to store that has tags, to store the tags for that article. Or if I want to have an order, I need an order line or an order item table to refer to everything that's in there. Or I need a course student table separately here because I can't put students inside of the course and I can't put courses inside of students. So I have to break this table out separately. Make sense? So it's really difficult because of that. And the way we actually build software, we build objects all the time. Like we think about objects, and it's very common in object-oriented programming to put objects inside of objects and arrays inside of objects or objects inside of arrays. It's very common for us to do that and think about our data that way. Make sense? So we have to inherently, if you're using tables, there's a lot of mapping you typically find you have to do between the objects as you want them in memory and the way they stored in the table structure, right? You typically have to do a lot of mental rigmarole to translate between those two. Make sense? And so if I want to, as we said, connecting information, if we want to pull it back together, I need a lot of complicated joins to do that. I need to take this data that's in the database, and if I'm using tables, I have to somehow map it back to objects, right? And so it's a lot easier, it would be a lot easier if my data in my database was actually stored as objects and arrays, then it's a lot easier to communicate back and forth because we're talking the same language. Does that make sense? Rather than having anytime I read data or write data, I have to translate back and forth between tables and objects, it'd be a lot quicker to be objects and objects on both sides. Make sense? That's part of what this gives us. And also, we deal with, when we translate objects, any operations that we do with the database has to be translated into SQL commands. If we're dealing with programming, we usually think of as methods, right? If I have a method, that's how you tell it to do something. But let's say I want to insert a record. Well, with SQL, I have to say, well, I can't just call it an insert method. I have to build up an insert statement and then tell it to execute that statement, right? So I have to do a lot of string manipulation is usually what we get into, is you have to build up a string, which is the SQL command, and then run that SQL command, which becomes non-intuitive and leads to some issues because, well, now your code refactoring tools don't work so well because you're dealing with strings, and it also opens you up to security issues like SQL injection attacks. And because it's easy because when you're dealing with SQL, well, your code is text. It's very easy for a hacker to put text into your code if they're both text, right? You think about, a text field that you have. If you're not careful, the user can just say, hey, I'm going to type in my username. I'm just going to take that username, put it in my SQL statement, and now they can run whatever code they want. It's really dangerous, right? And so, but we have to do this mapping, right? We think about methods and more over there, but we have to translate SQL. We become very vulnerable to these code injection attacks because SQL is text-based. We prefer something that actually isn't text-based. There is a workaround in SQL called prepared statements. Like prepared statements is what you need to do to avoid SQL injection of text, but it's still kind of hard because you still end up needing to generate this text to tell the database to do the thing, right? Whereas really what I want to be able to do as a developer is I want to be able to just call methods, right? And so, there's a lot that goes into there. In fact, if you deal with a relational database, more often than not, you'll find yourself writing a whole bunch of classes just to translate, just to map between the database and the application data. When I taught this with .NET, it wasn't unusual for in like our final projects, we might write 20 classes just to get data out of the database, and into and out of the database. Because you have to write a class for every single table that you have, plus another to represent the another one to represent the connection itself and things like that. So it can very quickly get out of hand. There's a lot of extra boilerplate code that you have to write to make that happen. Make sense? So we're trying to get away from that. We're trying to not have to write a class for every single table. Cool? It's one of the things we're trying to get away from. Because that's a lot of boilerplate code, as it turns out. So traditionally, the tool that we would use for this, because that's such a bear to do it and do it every time you're working with a new database, we'd use a tool called an object relational mapper. Short, we call it an ORM. And so what it does is an ORM framework. It gives you a layer between the database and your code. You write the code up here, ORM sits in the middle, database is down here. And so an ORM, what it actually would do is it would give you methods and objects, and you could work with that, call the ORM, and it would look like you're writing regular C# code or JavaScript code or whatever. And then at the bottom, it would actually be generating all the SQL for you. Does that make sense? So this is one tool that we used because it was so hard to do that translation, and because there's so many things that could go wrong. So the idea was to do that. Problem is they remove you from actually writing the SQL. Because you're not writing the SQL, you don't know what SQL it's actually writing and running, and that turns out to be a problem. Because there's a lot of things you can do if you have actual access to the queries that it's running. So that's actually turns out to be a problem. And my experience with the ORMs is they tend to hide a lot of performance problems. They make something look like, oh, it's an easy line of code. Oh, but guess what? That one line of code took down your entire website because it took an hour to run, or because it used so much memory that the server ran out of memory. It's really hard to see those things if you're working with an ORM, because it hides a lot of those details, right? Rather than you writing the queries yourself. That becomes a problem. And they also, often my experience is because they don't fully understand the SQL that you're writing, they don't fully understand the flavor of SQL that you're writing with your database, they may not understand some specific things that you can do with your database to make it more performant, optimize the performance. So for instance, Entity Framework actually doesn't fully understand all the performance flags that I can use with Microsoft SQL. There's a lot of things I can do when I'm writing the SQL that I can't do when I'm using an ORM. It just doesn't allow me to specify those things, including something as little as like Entity Framework and Link actually doesn't fully support left joins and right joins. You can do cross joins, but it doesn't support fully left and right joins, which is so weird. But there's things like that. Okay, so the theory is that part of the theory why ORMs became so popular is that, at least the theory was, that it would make it easier for us to migrate from one flavor of DBMS to another, right? If I'm not writing a SQL directly, then maybe it's easier for me to shift from, say, Microsoft SQL to MySQL to Postgres to Oracle, and I won't have to change any code. But in reality, that never worked. And in reality, in reality, that rarely happened, because shifting a DBMS is so hard just from a business perspective. It's like, okay, you want me to change the database and move all the database from this system to that system and avoid losing it? Basically, your business is very unlikely for that to happen. But unfortunately, because your ORM becomes so integrated with your system, it's actually really hard to change an ORM. In fact, it's a lot easier. It turns out it's a lot easier to swap out a database than it is to swap out an ORM, because an ORM becomes more ingrained in your code. Make sense? So that's just one thing to kind of be aware of. That's an issue that we've had with relational databases. We try to use this to solve the problems, but in turn, it actually has created a lot more problems. Okay? So things to understand. Some databases, namely Postgres, has finally started to add some JSON data types. So it does support JSON data inside of the relational database, and that is, some people are using that as kind of an alternative to fully switching over to a NoSQL database, is they're using JSON within their relational database. Specifically, Microsoft SQL has supported XML types for a long time in its database. As last I heard, it hasn't supported JSON yet, but they've supported XML, which you can kind of get a lot of the benefits from that, but not fully supported it. So there's still a lot of things that I can do with Mongo that I can't quite get if I just say, hey, I'm going to sort as XML in Microsoft SQL. And because it's not the main focus, that's kind of the gotcha, I can take a relational database and I can start adding JSON columns to it and get some of the benefits, but because it's not the main focus of that database, I can't get all of the things I do with something that's specifically built for. Does that make sense? So just some things to kind of understand in terms of the discussion. Okay. So overall, in the end, the way I see the world, and this is maybe my perspective a little bit, is that I don't think that relational databases are really optimized for today's applications. I think that there's still, I kind of understand the reason why they're still in use today, but I don't really think they're the best choice for a lot of cases. Okay, not really optimized for what we need. So relational data, kind of comes down to three things. Relational databases can't really handle more than a few thousand concurrent users. That's really their upper limit. It's really hard to push your relational database beyond that level. When in reality, in fact, we had a really hard time getting more than 100 concurrent users without the thing kind of falling apart. We had to do a lot of tricks and a lot of work to try and work around a lot of the issues to get to that point. So that's a big issue. There's a point where you get with relational databases to say, hey, we just can't handle more users. There's a hard limit, and so that's an issue. They're not really designed for optimizing distributed servers. I said, kind of the biggest you can get to is 3 servers max, when I really want to be in a lot more than that, ideally. And those 3 servers are really hard to set up. There's a whole bunch of bottlenecks and things you have to deal with just to even make that happen in the first place. And you're going to pay some more money because you have to buy a more pricey license even to use that feature in some databases. And you need a DBA to set it up in the first place because it's really hard to do. The other side of things is we're dealing with, unstructured, nested data. These are really things that relational databases were not designed for, right? You're designed for working with scalar values. Cool. So some of them, like Postgres in particular, has started supporting JSON, but a lot of them still don't support nested arrays and objects, right? And that is a really big thing. Okay. So that's kind of an overview, and hopefully you kind of understand some of the motivation for making the switch, okay? You kind of understand why we're choosing to cover Mongo here more and spend more time with it than spending time with MySQL, okay? There's some really strong arguments for using a NoSQL database in modern and real-world applications. So I need to talk a little bit about some of the terminology and some of the differences that you're going to need to know as you're building out your databases. And so we're going to talk about some of the differences in terminology. Okay, so we're talking with MySQL. We talk about schemas, we talk about tables, we talk about rows, we talk about columns, and we're saying fields and cells. Okay, Mongo has some very similar terms, very similar concepts, as it turns out, but we use some different words when we're talking about these things. So in Mongo, we talk about a schema. Okay, you can talk about a schema, and that's kind of your database as a whole. Okay, now with Mongo, the database is actually schema-less. Okay, with MySQL, we had to define the schema up ahead of time and have that, agreement about what that schema is. So I can't run your script if I don't have your updated schema. But with Mongo, we don't even define a schema. There's not a schema defined anywhere. It's completely schema-less. So the idea of a schema is more of a theoretical concept. It's a schema in terms of the rules that we are choosing to follow in our software. We've defined what the columns and the rows should be, but the database doesn't enforce that schema for us. Does that make sense? So in terms of Mongo, we will document that schema in our ERD, but it won't be enforced by the database. That's the difference, okay? Which means that it actually is a lot easier to change that schema because you just change the software and it works, more than likely. We talk about collections. A collection is a set of documents. A collection is, in a lot of ways, it's very similar to a table, okay? A collection is kind of like a table. You can think of an array like an array. It's an array of documents. A collection has a name, just like a table has a name, but the difference is it doesn't have a schema. You don't have to call create table to make a collection. You just add records to it, and suddenly you have a new collection. You don't actually have to make the collection. You just start adding records to it. Within those collections, we have what we call documents. Documents are kind of like rows. You can think of it as records or entities. But a document is an element within that collection. Okay? We can also have sub-documents. So a sub-document is an object that's kind of inside of or nested inside of a larger document. Okay? So I can put objects inside of objects. If I do that, then that's a sub-document. Documents are at the root. Anything inside of there any objects inside would be considered a sub-document. Okay? And I can actually nest sub-documents effectively infinitely deep. I can have object within object within object and within object. That's okay. When we talk about fields and properties are kind of your equivalent to a cell over in the database, over in relational database line. So your objects, your documents, they have properties. Okay, so a property has a name and it has a value. So for instance, I could say you have the first name and it has a value of Paul. I can have the last name property and it has a value of Smith. Okay? So determinants actually transfer over very similarly. They're pretty natural. In fact, if you think about these, they're very similar to the kind of terminology that you've seen with OO and objects and classes and object-oriented programming. It's very, very similar. Okay? When we're talking about schemas, I said some of this here. If we're working with MySQL, it has to be strictly defined at the beginning. We can't do anything until we've created all the tables. We can't put any data in there until the tables have been created. Whereas, with Mongo, you actually technically never have to define a schema. You can just start putting data in there without defining the schema of that data. You should take some time to create an ERD and plan out that schema, but you don't have to write any code to define the schema. Does that make sense? There's no code necessary that you need to keep up to date about the schema, but you should keep a diagram that at least documents what it is. So you want some documentation, but you don't actually have to create code for it. We're talking about the schema in MySQL. We actually need to build out a schema that accounts for future growth and future growth over the next 10 or 20 years. That's our target. If you're building a relational database, you have to plan it ahead of time. You're planning out 10 to 20 years, which isn't really practical when we're doing changes. We're doing agile development, and we're changing the requirements every 2 weeks, and we don't know them ahead of time. That becomes very hard. So in the world of Mongo, we just say, hey, we need a new collection, we'll add a new collection. We need new fields, we'll add new fields, and they just get added. We just add them whenever we need to. We don't have to update the schema. We just say, hey, we're going to add a new document, we're going to add a new collection, we're going to add a new field. No problem. Over here, if we have that schema, we have to keep it up to date. Anytime we want to make changes, we potentially need to run those alter statements to alter a table. We may need to drop foreign keys. We may need to drop and recreate foreign keys. We may need to drop and recreate indexes, all these kinds of things in order to make changes to the database. There's a lot of different things that you have to do in order to make it happen. Okay. We also have to, in the world of MySQL, if you have a table, all of the rows within that table need to have the same column and the same columns and the same data types. You can't have like, here's a row and his grade is an A, and here's another student and his grade is 4. It has to be all the same data types. So like it's a letter or it's a number, not both. Or I can't say, hey, here sometimes it's an integer and here it's a floating point number. That doesn't work, right? And they all have to have the same columns, the same data types. Make sense? You've kind of seen that already a little bit. That's not the expectation over there. But in general, and we haven't done too much application writing yet, but because this schema is so nailed down, we tend to write applications that actually break anytime we make the schema. Because we're expecting all that data to follow this rigid format, we bake those expectations into the code we write. Is actually very, very normal. In fact, if you look at writing a SQL query, if the schema is different, more than likely your SQL statement is going to fail. If you add or remove a column, more than likely that select query or insert statement is going to fail because, well, it doesn't obey the requirements anymore. So it's very easy for you to make a schema change and your application to break. Make sense? We don't really want that, but that's what that strict schema does for us. Is it says, oh, you're doing invalid data, stop. You can't go forward with this. That's pretty common. So over here, schemas don't have to be, I talked about some of this. Within a collection, remember a collection is kind of like a table, the documents can actually have different fields and different data types, which means that technically in Mongo, you're allowed to do things like have a student. This student has a grade of A, and this student has a grade of 90. Like, that's legal, okay? You just need to understand that. That is legal. The upside of that is it allows you to write code that is more resilient, because what happens is you say, at some point, maybe you build the first version, and you say, we're going to store the grade as a letter. And then later you decide that was a bad decision. And so we change the code, and now the code is storing it as a number. But I can still keep that data around, and I can say, okay, well, I have old data that's storing the grade as letters, and I have new data that's storing it as numbers. That's fine. I'll just write some code that handles both of those and doesn't crash if it's a number or a letter. Okay, no big deal. That way I don't have to lose all the old data. I can handle all the old data. I don't have to try and somehow figure out how to turn the A into a number, which is not possible, right? I can't go back from an A and say, well, this is 90 or 95, or I can't disambiguate. I don't know what the original number was. Same way with B. What was the original grade? I don't know. But it supports that. So does that make sense? Like, that's the value of having the schema be flexible, is that you can have different documents in there that don't necessarily follow the schema, but that means you write your software to kind of account for that. Does that make sense? You have to write software that's more flexible, more tolerant to differences in the schema. Cool? Which is really a good thing, right? It's a good thing to plan for those changes and be tolerant to them. And so, because you're dealing with this, and because generally speaking a change in the schema doesn't cause the application to crash, it's a lot easier to deal with that data that's old than it would have been in a relational database. Your insert isn't going to fail because you forgot a column. Your select isn't going to fail because that column doesn't exist. It's just going to go through and you'll get null or undefined. You'll get undefined for that column. It's all fine. You just deal with your code and say, I'm happy, and I'll put an if statement in there. If that column isn't there, then we just won't show that data. Cool. So it really forces you to write applications that are more tolerant, which in the end I think is a good thing. In terms of required fields and null, in MySQL we can mark columns as not null, and otherwise it's going to assume that they're null. So you can say that these columns are required. That doesn't exist over in Mongo. There's no way to say that something has to be required. Everything is optional. And so that comes back to this whole schema thing of saying there's not really a schema. Different documents can have different columns. So you just have to deal with that, right? If you need something to be required, then you need to enforce that in your application. Which turns out it's not that hard. Turns out it's not that hard to say, okay, let's make sure that the user entered values into all of the fields. Turns out we had to do that anyway. We had to do that anyway, because if we didn't do that with a relational database, you didn't say, hey, did you enter all the fields? We'd ship off the insert statement to the database, and the database would throw a very cryptic error saying, hey, there's no default value. Can't turn back to the user and give them that error. So you end up saying, oh, something went wrong. Or you have to do all the checking in your application anyway. So it's really not a big deal. It actually turns out to be less code. It turns out, or less code or the same amount of code, because we already had to check for required fields in our code anyway. Make sense? So it's not a big deal. It's actually not a big deal. And it's worth knowing that that's not there. There's no way to make a field required. When we're talking about primary keys, over in the world of MySQL, you can use auto increment, you can use a composite key, which is a combination of different columns, or you can use a UUID. As I kind of mentioned previously, the UUID would be preferred, and that would look like this. Over in the world of Mongo, there's a little bit more restriction. So in Mongo, the primary key always has to be named _ID. Write that down. The primary key has to be named _ID. You have no flexibility with that. Has to be _ID. There's no way to rename it. There's no way to choose a different name. The primary key has to be named _ID. It's baked into Mongo. Okay? Okay. Now that primary key, it can either be a unique string that you come up with whatever tools that you have, or it can be what they call an object ID. So Mongo provides a way to generate these object IDs basically randomly, and you'll get a string like this. Make sense? So those are your options. There is no auto increment. You can either come up with a unique string yourself. For instance, that might be the username. You might use the username as a unique key. You could use the email address as the primary key. That's all okay. Or it might just be some randomly generated string. So for instance, a really popular tool to use is something called NanoID to generate a random ID. And so we can do that way. Cool. We'd actually do composite keys as well. What we usually end up doing, if we want a composite key, I might do something like take the course ID, take the course ID, put an underscore between it, and then put the student ID. So that'll give me a long string, but it has both the course ID and the student ID. I can use that as my primary key. And that's a way I can get to a composite key. Cool. So kind of inherently in there, it sort of supports composite keys, but not necessarily directly. You can make it work, and actually that's perfectly fine. Cool. Sometimes that does come up. Dealing with foreign keys and relationships. So with MySQL, we said let's add a column. So for instance, over in the course student, we added like a student column, and then we added a foreign key constraint to enforce that relationship. Okay, that's the way we did that. Over in the MongoDB world, we add a field to the document or object to store the primary key of another document. Kind of like what we did here with the adding a column. But then there's no way to enforce it. That's the difference. And as I kind of talked about in the preface to this, that's actually a good thing. It's a good thing that it's not enforced because it turns out to be a lot faster if you don't enforce it. There's a big difference in performance by not enforcing it. Or if you want to do a relationship, you have the other option to just nest the related document inside, which actually often turns out to be even a better solution. Just say, hey, this other thing that I'm related to, I'm just going to put it inside of me rather than making a separate document entirely. Cool? So both of those are possible. Unique constraints. MySQL, remember, provides a way to define a unique constraint. So you can say like, hey, everybody has to have a unique email address, or everybody has to have a unique username, or everybody has to have a unique first name and last name, or a unique address, or whatever you want to force to be unique. You can do that. In terms of creating a unique constraint, that can be made up from one or more columns. And as far as that concerned, that unique constraint says for each row in the table, that unique constraint must be true, right? So whatever group of columns you pick, that needs to be unique within the table. And then all rows must satisfy this constraint at all times. Mongo does provide a way to add basically unique constraints, because it turns out to be something that actually is still valuable. But we do it with what's called a unique index. So instead of creating a unique constraint, it's a unique index. So we'll talk about that when we talk about creating indexes. Okay, when we go over indexes, that's how we do it. We have to create a unique index and add it to the collection. They can include one or more fields, and just like you can do that with the relational database, it must be unique for each document in that collection. Okay, document within the collection, kind of like row within a table. Very similar. And again, at all times within that the documents in the collection must satisfy that constraint. They must be unique. You can't do an update, insert, or a delete that would cause that constraint to be violated, to cause it to not be unique. Okay, dealing with indexes. Indexes are added to tables, or indexes are added to collections with Mongo. They're used to speed up select queries and joins and order bys over here. And over in the world of Mongo, we add collections and they speed up finds, or filter and sort operations of that sort. So same idea. Indexes are really the same idea. They're really important on both sides. I'd say especially over here, they're really, on both sides, they're vital to performance. You're going to have a slow application if you don't add indexes, but they're really important over here in Mongo. If you don't have indexes, it will be a whole lot slower than a relational database if you don't add any indexes. Okay? Because they're what make up for a lot of the choices that we make. They're what make up for a lot of those differences. Okay, so that's kind of your introduction, so you have some understanding of the terminology. Okay, so we're talking about schemas, we're talking about collections, we're talking about documents. Okay, and that's kind of your different understanding versus we talk about tables and rows. But it's very similar. So what we're going to go through is now the software that you need to get installed in order to be able to use MongoDB. You've already installed some software for MySQL. We're now going to deal with installing the software for Mongo. So I'm going to tell you about what some things that you need to install. Each of these are going to link to the download page. And then as part of the group exercise, I'm going to set you guys free to do that in your group exercise. Okay? So you'll need to download the community server. The community server is freely available for you to download and build applications with. It's going to run locally on your machine, kind of like MySQL Community Server is what actually hosts the data. Okay, so it gives you a local database that you can work with. The next thing you want to install is Compass. MongoDB Compass is basically a GUI for working with MongoDB. It's very much like Workbench. Okay, it's just like Workbench is a GUI for MySQL. Compass is a GUI for Mongo. Okay, you'll want that. You'll also want to install the shell for Mongo, and specifically that's what your lab is going to ask you to use, is work with the shell, as well as the quick start guide. And that allows you to query and update the database using your terminal, okay, using your command line. It gives you a chance to test queries and test operations and such. It's worth noting, and this can be a little bit confusing, the shell has a slightly different syntax than what we're going to use in JavaScript. They're very, very close, and so that's part of why I want you to use the shell to get used to it, because it will help you learn the syntax that we're going to use in JavaScript. But there are some slight differences which can get confusing when you're dealing with the documentation. Just a heads up. Okay? So when you're looking at the documentation, do be forewarned that there's a separate section for the shell and a separate section for how to use it in Node. And they're not always exactly the same, but they're, again, very close. Okay? There's also Atlas. Atlas is a cloud-hosted version of MongoDB server. So the community server is something you can download and run on your computer and have the database on your computer. Atlas is a way to have the database out there in the cloud. It's actually free, which is great when you want to deploy your application and have it running and have it a way where other people can use your database. Okay. I absolutely want you to sign up for an Atlas account and get an Atlas database up and running. We're going to end up, for the big project that we're doing this semester, the bug tracker, we're going to be using Atlas as the main go-to for that project. Cool? So definitely want to get an Atlas account set up. You can use it during testing, which is really helpful for eliminating kind of this need to migrate your data between your local system and the production system. So sometimes I'll do that straight up for small projects. And keeping things in sync, so that can be really helpful. I tend to, at least with my small projects, I tend to actually use this as I'm developing software rather than just waiting till when I deploy it. If you're curious about pricing on Atlas, this is kind of what their pricing was. I pulled this a few months ago, so I don't know if this is fully up to date. Let me go check the slide to see if the prices have changed. No, they're basically the same thing. There's a preview there. Serverless. Okay, so they're coming up, oh, because they've moved it around. Okay, that's why. Okay, so they've changed it a little bit, but I'm going to stick with that. So there's kind of a shared cluster which starts out free. This is a free plan you can use. It actually runs on top of AWS. So it'll actually run this in AWS for you and give you a nice management for it. It's limited up to 512 megabytes. It's worth noting. Your database can't get bigger than 512. That includes all your documents, all your collections, all of your indexes. Total will have to fit in 512 megabytes. That shouldn't be a problem for this course. I've hit that limit with some personal projects, but suffice to say that personal project was using up quite a bit of data. Namely, I think you guys saw over summer there was a system that was sending you emails every time you submitted code. Yeah, that one I hit the 512 mark, and that's part of why it went offline for quite a time. I had to change my code. So it wasn't saving some data that it didn't need to save. But you're probably not going to have as much data as I had in that system, suffice it to say, because you're probably not doing something that's adding data every time you're submitting code. So that's that. You can scale it up. It's going to cost you more if you go up to 5 gig. That's kind of the pricing range. If you're trying to do this for a real-world website, there's kind of your starting price, $57 a month, $95. This is really not that big. When you consider the average developer salary, that's a pretty small price to pay. So, just if you're curious what the price ranges are, that's what that looks like. Cool. Okay. So that's kind of your overview. You kind of understand what MongoDB is. You understand part of what the motivation is behind it. What I want you to do is break up in groups of 2 again. You don't necessarily have to break up in the same groups that you had previously. You guys can choose new groups this time if you want to, or stick with your previous groups. What I want you to do is you're going to go through and install these softwares. You're going to install the community server, you're going to install Compass, you're going to install the shell. You're going to install all 3 of those things. We also want you to go through and register for a MongoDB Atlas account. If you have any questions about how to answer the registration form, just see me and I'll try to give you an answer on all that. So you're going to get these things set up. You're going to start reading through the MongoDB Quick Start Guide that's over on Inside Rankin. Sorry, not Inside Rankin, on Perusal. So you're going to read through that. What I want you to do is create a courses database, right? Basically using the same data that we had before, right? So what data did we have in the relational database? Well, kind of as a refresher, you're going to have teachers, you're going to have students, you're going to have courses, you're going to have assignments, and you're going to have grades. So what I want you to do is figure out how to take that data, how to model it, how to put it into a MongoDB database, namely to capture the data for your AWD 1000 course and for this course.